Hi folks, we're going to take a look at number 11 from page 206. So they give us this function here and they're asking us to find this constant b. So they tell us that b is just a constant. Okay, and just to explain exactly what this means, it's just shorthand. So it says find the constant b such that there exists a point of inflection at the x value 3. Okay, so st such that, and this just represents there exists. Okay, so what we know here is that this function is going to have a point of inflection at x equals 3. So we know we're going to have to work with the second derivative, and that means that at x equals 3, the second derivative is going to either be equal to 0 or perhaps might not exist. Okay, so we'll see what happens, but let's start by finding the second derivative. And of course, to find the second derivative, you first have to find the first derivative. Okay, now just a reminder here, if you still need to convert these into more user-friendly forms, that's not a problem. So here I'm going to think of this as x plus 1 to the 1/2. And here I'm definitely not going to use the quotient rule. I'm going to just think of this as b times x to the -1. Okay, it's going to make finding the derivative much easier. Okay, so first let's find the derivative of this thing, and we have to use the chain rule. So this is like our u. So u to the 1/2 is 1/2 u to the -1/2. So 1/2 x plus 1 to the -1/2 times the derivative of x plus 1, which is just 1. Okay, now notice how I still actually write that out. And I just do that so I don't forget that I'm applying the chain rule. Because if this had been 2x plus 1, well, I would have been multiplying by the derivative of 2x plus 1, which is not just 1. Okay, so I would strongly recommend that when you're taking these derivatives even quickly, to always fully write out the chain rule. Okay, so here in the next one, well, b is just a constant, so it's just plus b times the derivative of x to the -1, and that's easy. It's just -1 times x to the -2. Okay, now I have to find the second derivative. So normally I would be tempted to first simplify the first derivative before finding the second derivative, but finding the derivative of this function is so easy in its current form that I'm not going to actually simplify first. Okay, so you want to start, thinking about when it's necessary or useful to simplify and when it's not quite so necessary. Okay, so I'm going to take the derivative of this function here now to get the second derivative. So the 1/2 is just a constant. Okay, and now I have to take the derivative of x plus 1 to the -1/2. So again, a similar chain rule as above. It's going to be -1/2 times x plus 1 to the -3/2 times the derivative of x plus 1, which is just 1. Okay, so here I've got my b times -1, so I have minus b is just a constant, and now I take the derivative of x to the -2, which is just -2x to the -3. Okay, so let's now take the second derivative at 3. Okay, and see what happens. So see if it's even possible for it to not exist, and if not, it means we need it to be equal to 0. Okay, so as I'm inputting 3, I'll also simplify this expression. So I notice in this first part, everything is going to go to the denominator except this -1. Okay, but everything else, 2 times 2 is 4, and here I'm going to have x plus 1 to the +3/2. Okay, oh, except, sorry, I forgot, we're applying this at 3, so we might as well replace x by 3 there. Okay, and so here I've got -b times -2, so I'm left with plus 2b in the numerator, and this expression is going to go into the denominator, so it's going to be x cubed, but I know that x needs to be equal to 3, so 3 cubed. Okay, so the first thing I realize is that nothing's going to give me 0 in the denominator, so I know that f double prime at 3 looks like it's going to exist. Okay, there's no value for b. Had b been in the denominator, we could have said, b can't be 0, or b equals 0 gives us a second derivative that doesn't exist, but that's not the case. So we know that f double prime at 3 has to be equal to 0. Okay, so now let's just solve for b. So what do we have? We have -1 over, so this is 4, okay, to the 3/2. Okay, now remember how we solve these here. I can do one of two things. I can first cube it and then take the square root, or first take the square root and then cube it. But it makes a lot more sense to first take the square root because it makes the number smaller, and then cube it. So I'm just left with 2 cubed is 8. So I've got 4 times 8. Okay, and then here I've got 2b over 27. Okay, so here let's add these two fractions. Okay, so here that becomes negative 27 plus 32 times 2 is 64b all over whatever this is, 32 times 60 times 27. I don't care what it actually is, because I need to solve this fraction for when it's equal to 0, and the denominator doesn't come into play. I know for this fraction to be 0, the numerator has to be 0. So I need negative 27 plus 64b to be equal to 0, and so 64b is equal to 27, and so b needs to be equal to 27 over 64. And there's my answer. Okay. So, fair bit of algebra, but let's recap the main ideas here. So the main ideas is you have a function that needs to have a point of inflection at x equals 3. So that means you have to find the second derivative and then evaluate it at 3. Now, of course, because you have this unknown, you end up with, an expression that still has a variable in it. And because in order to have a point of inflection, the second derivative has to either not exist or be equal to 0 at that point, we saw that it definitely was going to exist. So the only option was that the second derivative was equal to 0 at that point, and they gave us an equation that we could solve